Hello, everyone. My name is Brendan Hill, and I'm presenting our work, Communicating Plans, Not Percepts, Scalable Multi-Coordination with Embodied World Models. This is a collaboration with my colleagues from the National University of Singapore and the University of Wisconsin-Madison. I want to start with our bottom line. In multi-agent reinforcement learning, there is debate. Should we let agents learn their own language from scratch, or should we structure it? We found the emergent communication fails at scale. Vibrant grows complex, success rate drops down to 13%. However, when you equip agents with explicit world models, allowing them to communicate their future plans rather than their current observations, we achieve robust coordination with greater than 96% success, even in complex, partially observable environments. We investigate this using a cooperative task allocation problem. We have a grid world with two agents and two goals. It's partially observable. Agents can't see the whole map, only the area near themselves, and they can't see each other. To solve this, they have to agree on who goes where. We compared two distinct approaches to solving this. Our first approach is learn direct communication, or LDC. This represents the emergent philosophy. Here, we have agent A receiving inputs, which are processed by the input layer and passed through hidden layers. The policy head outputs a movement action and a message. Crucially, this message is just a binary bit, a 0 or 1. We don't tell the agent what it means. We train the whole system end to end, hoping a protocol emerges solely from the shared task reward. In further experiments, which we go into here, we determined that increasing this message space decreased performance as it almost acted as a noise to the agents. The agents exchange these bits at every time step, attempting to coordinate their movements. So did it work? In small environments, yes. These heat maps show the probability in action given a received message. You can see a strong statistic of dependency. For example, if agent 1 receives a 0, they're likely to go up. If they receive a 1, they go left. A protocol did emerge. As we'll see later, this fragility breaks down when the state space grows. To address this, we developed our second approach, intention communication. This relies on an engineered inductive bias, the world model. The agent takes its local observation and encodes it in an initial latent state, which feeds into a shared policy head to determine the current action. This action is produced the same as with learned direct communication and does not involve the world model. But here's the innovation. We introduce an imagined trajectory module. Using the agent's current policy in a learned transition model, the agent forms a mental simulation, a rollout of its own future trajectory, including a shared policy head, transition model, and the next latent state. This will pass in a loop for multiple steps, so the agent can stack the future states. We then pass this imagined land into the message generation network. Using self-attention, we compress this complex directory into a compact message vector. This allows the agent to explicitly communicate its intent, its plan, to a schema rather than just a vague bit. The self-attention is then compressed with mean pooling. Data is extracted through hidden layers, and then message heads generate the actual message sent to the message output. Let's look at the scalability comparison. In a 10 by 10 grid, the baseline fails completely. The emergent LDC model blue manages about 30% success, while a world model approach achieves 99.9% success. We scale this with 15 by 15 grid, the state space expands massively. The emergent model collapses near random performance at 12.2%. The crit assignment problem is just too hard. They can't learn a language from sparse rewards in this large space. In contrast, intention communication holds strong at 96.5%. By decoupling the dynamics learning from the policy learning, the system remains robust. In conclusion, our results highlight critical trade-off. The emerging communication is theoretically elegant, robust, scalable embodied coordination, engineered inductive biases, with the predictive world models that vastly outperform emergent protocols. Further, this method is highly sample efficient. We achieved these results under strict computational constraints, which is necessary for developing real-world embodied AI, where interactions are costly. So next steps. Move forward, let's integrate stochastic world models like BAs or diffusion. Handle uncertainty. We are working on scaling this from grid worlds to high fidelity physics simulators like Isaac Gym. Thank you for your time. If you're interested in the details, please check out our full paper.